Hello, my name is Thales Silva, and in this short presentation, I will talk about my current research on self-supervised learning for computer vision. This is my ongoing work for my master's degree with Professor Jean Ramirez as my advisor. You can find me on LinkedIn or read more about my topics of interest on my blog. I would like to start by talking about the current state of machine learning for computer vision and state the motivations behind self-supervised learning. In the last decade or so, the recipe for success for machine learning has been practically unchanged. The combination of large data sets, parallel hardware, and very deep models works amazingly well to solve various problems from classification to detection or reinforcement learning. The recipe is simple. Take a very large data set like the ImageNet, train a deep convolutional network on it, then use the pre-trained weights to solve downstream tasks like instance segmentation or pose estimation that do not have significant supervised data to learn a model from scratch. One important point is that large models trained on large data sets tend to learn representations that generalize well to other tasks. The ability to transfer knowledge from one task to another is one of the main factors behind the success of machine learning in both academia and research. The importance of generalizable and compact representations is key. A simple transformation to the input data from Cartesian to polar coordinates can change a problem from unsolvable to straightforward. That's because the performance of machine learning algorithms, mainly the shallow ones, highly depends on the representations they receive. However, scaling this recipe is not easy, and the main bottleneck is data annotation. If we only consider the classic tasks in computer vision such as image classification, detection, and segmentation, we see that as the level of annotation becomes finer, the amount of annotated data decreases substantially. Moreover, for some real-world applications, training a deep learning model from ImageNet pre-trained weights might not be the real solution. That might be the case for numerous applications in healthcare, where the number of non-annotated observations is far larger than the annotated ones, and the cost to annotate a single observation is substantially high. That's where representation learning fits in. Our goal here is to devise methods that can learn generalizable representations from raw data sets that don't require human labelers. In this context, self-supervised learning is an approach to unsupervised learning where the supervisory signal is extracted from the data. It usually requires the formulation of a pretext task that acts as a proxy in the learning process. That is, by optimizing a pretext task, the model learns useful representations that can be transferred to solve downstream tasks such as depth or pose estimation. Examples of pretext tasks include language modeling or masked language modeling. In fact, the success of self-supervised learning for NLP was one of the main motivations to expand such techniques for vision, where we have image painting and next frame prediction as analogous pretext tasks. Other famous pretext tasks include the exemplar pretext task and the relative patch prediction pretext task. In the first, the idea is to treat each example as a unique surrogate class. Say, if we have 10,000 images in a dataset, we will have 10,000 classes. However, we also applied have-data augmentation transformations to increase the number of observations per class. From this point on, this is just a classification problem optimized with cross-entropy, where each class represents the augmented versions of the same image. For relative patch prediction, the idea is to devise a prediction task to predict the relative position of surrounding patches with respect to a center patch. We can view this task as a netway classification problem optimized with regular cross-entropy. Other two self-supervised pretext tasks include jigsaw puzzle and rotation prediction. Similar to relative patch prediction, the jigsaw pretext task poses a prediction problem where a set of patches from a given image is shuffled, and the network is tasked with the challenge of predicting the correct permutation used to shuffle the image patches. On the other hand, the rotation prediction simply devises a prediction task where the network is trained to predict which rotation angle from a set of valid angles was used to transform the input image. These pretext tasks show the benefits and potential of self-supervised pre-training. To have an idea, self-supervised pre-training of an AlexNet model with the rotation prediction pretext task on the Pascal-Vogt 2007 detection task achieves an MAP of 54.4%, which is only 2.4 points lower than the supervised case. However, devising and optimizing pretext tasks, like the jigsaw or relative patch prediction, imposes the problem of devising the task itself. It resembles a manual process where there is no guarantee that optimizing for a given pretext task will make the network learn generalizable representations. Nonetheless, most state-of-the-art self-supervised learning methods optimize an instance discrimination pretext task using Siamese networks as the main architecture. In this context, one of the most popular loss functions is the InfoNCE loss. The InfoNCE works in the embedding space and aims to learn similar embeddings for different versions of the same image, also called views, and learn different embeddings for representations coming from different images. To avoid a trivial solution where the network learns constant embeddings for all images, the InfoNCE loss contrasts a single positive observation with many negative images. Different ways to avoid trivial solutions for self-supervised learning have been proposed. One idea is to only propagate gradient updates through one branch of the Siamese network at a time. With this approach, even a simple loss function, such as the mean squared error between embeddings of the same image, can produce highly generalizable representations without the necessity of comparing an anchor image with negatives. One common way to assess the quality of self-supervised representations is to measure linear separability of the learned embeddings. Usually, we append a new classifier head on top of the pre-trained self-supervised model and fine-tune it on a classification task such as the ImageNet 1K classification. Self-supervised methods have significantly reduced the gap between supervised and unsupervised pre-training. In fact, for many downstream tests such as detection, segmentation, depth estimation, and others, self-supervised pre-training already surpassed supervised pre-training by a considerable margin. Taking all this context, our work, Consistent Assignment for Representation Learning, or CARL, seeks to combine ideas from self-supervised learning and deep clustering. If we view the instance discrimination pretext task from a clustering perspective, we see that the learned clusters only contain representations from synthetic views, and therefore fail to capture semantic structure from the data. In other words, a cluster only contains augmented versions of the same image, and the loss function such as the InfoNCE is optimized when a cluster contains all different views of the same image and the different prototypes are far away from each other. Instead of optimizing embeddings directly, we discretize the output space and learn general prototypes that serve as energy beacons in the optimization process. Note that these prototypes are not meant to learn the true class distribution of the datasets. That's why we term them general prototypes. The training model also follows the Siamese architecture. We begin by creating two views from the same image using stochastic random transformations like rotation, cropping, and color distortions. We then forward the two views independently through the encoder and the projection head. Here, the encoder is a regular ResNet 18 model without the classification layer, and the projection head is a two-layer MLP with nonlinearity ReLU. Once we get the respective representations for each view, We forward them through a shared weight assigner function and obtain the probability distributions of the views with respect to the general prototypes. Our consistency loss function enforces different views of the same image to be assigned to the same prototype. However, since the number of prototypes is smaller than the number of images in the dataset, a given cluster will not only contain different views of the same image, but will also group views from different images that are similar enough to be assigned to the same prototype. Once we get the probability distributions of the views over the prototypes, see equation 3, our similarity function is defined as a dot product between the normalized probability vectors of the two views. Note that if the probability vectors of the two views signal the same class with maximum confidence, the negative log is minimized. In other words, the consistency loss pushes the network to assign one-hot vectors for both views. However, only forcing different views of an image to have the same cluster assignment using our consistency loss leads the optimization process to a trivial solution where all representations end up assigned to the same cluster. To prevent such triviality, we force the distribution over the general prototypes to be uninformative by minimizing the callback label divergence with respect to a uniform distribution. Our regularization is shown in equation 4. Notice that P hat IC is the expected distribution over a mini-batch of size P. We can view this term as maximizing the Shannon entropy of the average distribution of the predictions. We can interpret the KL divergence as regularizing the encoder to encourage the approximate posterior to be closer to the uniform distribution. Minimizing the KL divergence will force the predictions of an image view to be spread across all clusters. Since we don't know the underlying class distribution in advance, the KL divergence acts as a prior, where we assume that the input observations are uniformly assigned among all prototypes. Then, our final objective is the combination of the consistency and the KL divergence term. In terms of results, representations learned by Carl tend to perform equally well or better than current state-of-the-art in some datasets. We compared our method with concurrent work on the CIFAR 10 and 100 datasets, on the STL10 dataset, and in the ImageNet dataset containing images of size 64 by 64. For the majority of comparison scenarios, pre-trained representations using Carl tend to perform better than other methods when training a linear classifier on top of the frozen representations. I'd like to thank my advisor, Professor Adin Ramirez, for all the support. And if you have any questions, please forward them to my email. Thanks.